But let us have this discussion, and we are still on electromagnetic waves, and we've learned that electromagnetic waves are basically a portion of that electromagnetic wave is light. So somewhere in the middle portion of that spectrum, because we call it basically as a spectrum because it includes so many other waves, no, or other kinds of rays, no. So there are those that have shorter wavelengths, and then there are those that have longer wavelengths, no, and they are called from radio waves up to gamma or cosmic rays, no. So they vary in their degree of energy, their degree of their value for frequency, and their value for wavelength. No? And we also characterize the wave as having uh, this amplitude, this wavelength, this frequency, these characteristics of a given wave. No? And and they have a specific speed, no? And since light is a portion of this electromagnetic wave, then it must have the same speed, no, as that of the visible light, the electromagnetic waves, no? So whatever is its frequency or its wavelength, no, its speed is kind of constant, no? And we know that to be around 300 million meters in every second, no, or something like 300,000 kilometers per every second. No? We understand that it can go around the Earth, no, in a very, very fast manner. So encircling the Earth or traversing the Earth's surface, no, it can cover it in what 8 times, no, in a matter of maybe of a second. So that's how fast light. But we understand that if the distance now becomes very, very long, no, like distances between galaxies, then it may probably take light to travel that in a year or more. No? So we have also a unit of distance or speed, no, we call as light years. So these distances are already enormous, no, and even though light is believed to be the fastest thing in the universe, then we notice that if the distance is so great already, then that the time or the time for light to traverse those distances may actually involve years, no. So again, looking at the relative nature of distances, no? So what we are seeing right now is our dimension. In our own dimension, we acknowledge light to be very fast. But again, in terms of distances like between galaxies, then again, that's a different way of counting the time for light to travel. We go to this discussion here, and we will understand that there are varied characteristics of our light. And one of the guy there that we will probably make mention is James Clerk Maxwell. And Maxwell has his theory, his encompassing theory. And perhaps you've watched that in the video of Professor Dave, the one I attached in our discussion as well. That James Clerk Maxwell is a very famous guy. Not really that famous like Einstein, but his understanding, how he combines the knowledge of light to magnetism and to electric field, made that a grand unifying theory, what he brought about. Now, what we learn about electromagnetic waves is that when there is an electric field, then it will also create something like a magnetic field as well. So we learned that in chapter 7. So in magnetic induction, when there is electricity, then you can produce magnetic field, or when you have a magnetic field and you let a current or a wire pass through that magnetic field, then current is created. So electric field and magnetism therefore are two intertwining principle. But how they move is that they move in a transverse manner. So this is a transverse wave. So if this is the electric field, the one in the red or relatively red marks here or brown, no? They are perpendicular, no, to the magnetic field that is indicated by letter B, no? So usually B there is magnetic induction or magnetic field, no? So whenever an electric field is created by an electric charge, no, a corresponding magnetic field then also results, no? But they are, no, perpendicular to each other, no? Now, the other direction here is now the speed, no, with which this magnetic electromagnetic wave is traveling, no? And it is indicated by a value c, no? That's how fast it is moving, no? So they were able to calculate this transverse wave, no, developed by this magnetic and its electric field to be around, no, uh, almost 300 million, no, meters in every second. So this value of the electromagnetic wave resembles now to the speed of light as well. So therefore we can say that the light is, no, is either the same as the electromagnetic wave, or, no, uh, they are separate, or they are either the same, no? Because they share the same speed, no? And again, in future discussions we will see that light actually, no, the visible light that we know is a tiny portion of this huge spectrum of the electromagnetic wave, no? So the electromagnetic waves contains those with long waves, no, or those with wavelengths that are a bit longer, and those that have shorter wavelengths, no? And again, this is the whole electromagnetic spectrum, no? Somewhere in the middle, no, something like 700 nanometer to, or 400 nanometers to 700 nanometers is this um, 7 colors of, no, our white light, no, or our visible light, no? Now we call this as the visible light because this is the only range of wavelengths that is able, no, to be detected by our human eye, no? So other than this, no, others are, the other wavelengths there are invisible to our eye, no? So this is now within our sense of sight, no? So we see that there are only 7 colors, but in reality, no, there are maybe, no, a million combinations of these colors, no? So as we transition from one, no, to the other, then maybe, no, there are a lot more there. Now the value of the speed of light there, no, which is indicated by c, no, and that is kind of constant. They believe this c value is the fastest speed in the universe. It's equivalent to the wavelength, no, of a given, no, spectrum of this wave, and then multiply it by its frequency, no? So wavelength in meters multiplied by frequency, no, maybe in hertz, now gives you a value equals to 300 million meters per second, no? So whatever is that wavelength and frequency, so long as you take it here, no, in our spectrum, then its value will always be a constant value equals to 300 million meters per second, or 300,000 kilometers per second. So here are the different, no, portions of this wave, no? So the different electromagnetic waves, and we've discussed that part of that wave is your visible light, no? And if you'll get a value that is around 560 nanometer, which is a wavelength, no, then it must be within the range of the visible light, no? Because the visible light is from 400 to 700, no, nanometer, no? So what's a nanometer? That is, no, dividing 700 by 1 billion, no? That's a nano value, no? 1 over a billion, no? So a very small length actually, no? So the longest of this length is your red color. And again, no, we call red to be a very striking color because it has the longest wavelength, no? Try to wear a red shirt or red attire, no, red clothes in a party, then you'll notice that everybody's head will turn towards you, no, because you will attract everybody's attention, no? So red, no, really, no, catches our attention, no? So just like the color orange is also, no, even if the object is kind of far, no, you will always notice somebody wearing orange, no? Okay, so again, no, orange is an attire worn by, no, rescuers, because you can always, no, see them even if they are in the middle of the ocean, no, floating. Okay, so like seamen or persons that are working in ships, they wear this attire that is commonly orange. So in case they fell off the ship, then they have a fair chance to be seen by other people who are trying to find them. Now here's a formula to find the frequency. So if C is equals to wavelength times frequency, then we can find frequency by dividing the speed of light by its wavelength. So for example, the human eye is sensitive to the electromagnetic waves that have wavelengths from 400 to 700 nanometer. So what range of frequency of electromagnetic radiations can be detected by the eye? So we are trying to find the equivalent frequency of 700 nanometer. So if the speed of light is constant at 300 million meters per second, and you divide it by 700 nanometer, so you will end up with a very high frequency. The frequency of the red color, which is 700 nanometer, is 4.3 times 10 to the positive 14. Whereas the shortest wavelength, which is violet or purple, will have a frequency of 7.5 times 10 to the 14th. Okay, now here are radio waves probably now, and it is broadcasting at 88 megahertz. So mega is 10 to the positive 6. So what is the wavelength of that radio wave? So 3.4 is a relatively big distance. So radio waves have wavelengths that are short or are bigger. So bigger wavelengths, because they transmit a carrier signal that maybe carries people's voices. So again, radio waves or those longer wavelengths are used in communications, like in broadcasting. So these are, again, ways of finding the wavelength or the frequency. Okay, so I think this is this is the slide that I'm trying to emphasize now, because this is not included in our previous discussion or video there. Now, light can be considered also as a stream of particles. So it has, again, a dual nature, dual characteristic. It is believed to be one kind of a particle. Light is believed to be a wave. So it follows the behaviors of waves. Like it reflects, it refracts. But at the same time, they also believe light to be consisting of streams of particles. So these particles of light is, if they will think of it as if they will quantize it, the word is quantized, they will make it into small bits of particles, that when a beam of light is focused on a stream of electrons, some of these electrons are being thrown away. So they term that as a photoelectric effect. So if they think not only light to be something like a kind of a wave, then maybe it will not affect the electrons that are being streamed. But it seems that something collides with electrons. That's why they are being thrown away. So again, if the electrons are moving from left to right and you go against the flow of these electrons using a beam of light, some of the electrons there will kind of get dislocated, or they will run away. So again, they attribute the principle for light to being a particle. So the particles of light are believed to be called as photons. So they term it as photons. So again, that phenomenon that explains why electrons are its energy, its behavior changes, its direction of flow changes, is due to this photoelectric effect described in an activity. So I think Einstein performed the given activity there. Now, here are some attempts of measuring the speed of light, and the closest value that they got way back in 1675. So perhaps the period here is not possible for them to measure the speed of light exactly because of the limitations of equipment and and the devices, no? So they don't have the right devices to measure the speed of light, no? But however, now they come close to a value equals to 210, no? 1,000 kilometers per second. And I think, no, that is way close already, no? Being short, of course, by 90,000 kilometers per second. No? So right now we know that it is 300,000 kilometers per second. No? Now the closest, another closest value is 310, no? 1,000 meters per. I don't know. This one, if this is in meters per second, this is kind of far already. No? However, if this is in meter, if it that's in kilometers per second, and then 310 may also be another close value. No? Anyway, no, those are some of the estimates that they did, no, on the behavior of light. No? Then geometric optics probably will now try to make use, no, of the idea that light eventually reflects, no, it creates an image. No? So when you're in front of a mirror, you will always see, no, a picture of yourself, no, in front, no, exactly like you. But sometimes, no, the right hand there is not the same as your right hand. No? So the image is kind of inverted. The image is kind of perverted. No? So these are things that we can describe. No, an image that we see whenever light is being passed through a uh, a reflecting surface. No? So that reflecting surface may be called as a mirror. No? A very smooth surface. No? So there are also varied ways in which light bounces off. No? So sometimes it bounces at a regular interval. No? They call it a specular reflection. And it may also reflect, no, in varied directions, no, depending on the kind of surface. No? So if the surface is kind of rough, then the reflected ray will be moving or traveling at varied directions. No? So we can think of it as a diffuse version of light. No? So they may call it as diffuse reflection. No? So again, depending on, no, what material the beam of light, no, will go through. No? We also have transparent materials. These are materials where light can easily pass through. There are also translucent materials where only where some of the light there will be traveling or will be allowed to pass through, but they may be made to move in varied directions. Again, and opaque materials. So geometric optics will also we have a specific chapter, by the way, for geometric optics, and we will try to learn there how the light behaves if the surface is kind of curved. So what if you are dealing with a mirror that is called a concave mirror? Now, how do you see yourself in front of a concave mirror? Or common mirrors that you also encounter are those that are found in the side mirror of a car. You'll see yourself there kind of small. But the advantage of the convex mirror is that you can see a wide range of angle. So even though you are driving, you can see an angle that is way off your what do you call that, lateral vision. So you can see a greater degree of angle while you drive. So I think that's very important when you drive. Some rules in driving that you have to always remember is that you use the 3 mirrors inside your car. So there are 2 side mirrors and then the rear view mirror that is directly right in front of the driver. So if you're a good driver, you always use those 3 mirrors. So your eye, although your eye is always on the windshield, looking at the road, you always keep a constant glance once in a while to all those 3 mirrors. So mirror images in driving is crucial for safety. That is, if you are an attentive driver. So again, a lot of that will involve reflection, and again, reflection can happen at varied ways. If the surface is rough, if the surface is flat or smooth. So for smooth surfaces, we have a regular reflected light. So these incoming rays here are sometimes called, no, again, incoming or incident ray. No? Those that are now bouncing back, no, or bouncing from the surface are called reflected rays. No? So you have incoming and you have reflected ray. No? Now, aside from the incoming and the reflected ray, there's always this normal line which is always perpendicular to the surface, no, that you measure the angle formed by the incident ray, no, and the reflected ray. No? Usually the angle here is believed to be equal. No? So this equal angle, no, this is known as the angle of incidence and the angle of reflection. This equation here that equates the two angles is termed as the law of reflection. So it is always based, no, in terms of this normal line. No? Now, whenever the surface is kind of rugged or rough, no, then the reflection now moves in varied directions. No? So look at how the reflected rays are behaving here. No? So we call this next diagram as diffuse reflection. Now, one picture also of reflection is that of the surface of the moon. No? So the surface of the moon, during full moon, of course, you'll see the full bright moon, no? But its light there that is reflecting on the surface of the moon is not even. No? There are portions of the moon that are, no, dimly lit. No? So sanag man siya pero hindi siya as bright as other portions of the moon. No? And again, no, when they try to examine why the surface of the moon, no, the whole surface, no, of a full bright moon, full moon, no, nga hindi parehas kasanag, is that they attribute, no, nga the surfaces that are relatively flat, no, inang made of sand, no, e may portion sa moon kuno nga puros lang gid plain sand, no. Okay, so ang ina kuno nga part amo nang medyo dulom, no, darker, but the rough surface or the mountainous areas, no, they are the bright parts of the moon. No? And again, if we think of specular and diffuse reflection, the diffuse reflection is, no, if we think of the moon, then this is the brighter reflection, no? Ang diffuse reflection. No? Whereas if the reflection there, no, is kind of regular, in terms of the surface of the moon, then amo ni siyang medyo dulom. No? Okay, so again, no, I think may aran sila ginatawag sa moon nga sea of tranquility, no? You know, flat lang gid nga made of sand. If you will view that, no, ang reflection sa earth, amo nang part nga medyo dulom gamay kuno, no? Masanag siya kay full moon, no? But that part, no, is not that bright, no, or strikingly bright, no, compared sa mga mountainous areas. Okay, so that's reflection. Now, another phenomenon of light is when light enters a surface, no, or from air, no, it goes into glass, or from air it penetrates water. No? You'll notice that there are now two medium that are involved. No? Now, the two mediums that are involved will cause light now to bend, no, towards the, no, normal line. No? So the light there will no longer travel in a straight line anymore. No? Now, although part of the light will be bouncing back, no, but again, no, a portion of it also will be absorbed or will be, no, entering the glass here. No? Okay, so again, no, two things happen, no, when light travels, no, through two different mediums. No? So this line here is called as a boundary. So once light reaches the boundary there, no, two things can happen. No? A reflection or a refraction. No? Now, why is there refraction? Why will light, no, travel in a different direction? Because light will be, no, changing its speed. So there's a speed of light before, no, it reaches the glass, and there is now another speed of light once it is now being, no, once it is now entering into the second medium. No? So the change in the speed there causes the speed, the angle here to change. No? Now, common examples of refraction is, of course, when you dip, no, a spoon. No? Try to dip a spoon in water, you'll notice it to be bended. No? So why is there bending? Because again, no, the light that comes from the spoon and going to your eye now is, no, change its angle. No? Okay, so again, we will see that with another example. Now, this equation here that is used for our refraction now is known as the Snell's law. So there's this index of refraction that is usually solved, n, or the index of refraction is solved by using the speed of light and the speed of light in a particular medium. Okay, so when you get the ratio, then you will have an n value. So again, if I think if the speed changes from one medium to the next, matiko na siya, and if the medium is much denser, when you say much denser, mas intact daw ang iya particle. So like air is less dense, glass is more dense, that the bending will be now towards the normal line. So manotice mo mas lapit, mas gamay ang angle of refraction sa dalom compared sa angle of incidence. So again, there are still two angles that are involved here, but it's not the same as the angle of reflection. So angle of refraction. Okay, so these are the different indices, index of refraction. So for different materials. So for air, and for those that are solid materials. So we know therefore that if you have a prism, so if you have a glass that is shaped like a pyramid, and you beam light into that pyramidal shape glass, then light eventually will bend due to refraction. And we call this now as dispersion of light. So one white light or one visible light will now bend into different colors, and what you see now are the different colors that's maybe looking like a rainbow. Okay, so again, we call this as the dispersion of light. So it will involve your principle of refraction. Now, another common example of dispersion of light is the tiny droplets when there is what drizzling. It's drizzling, nagapanalithi lang ang gagmay ginakaayo. So when there's a drizzle, mas may pa ganiyang drizzle kay makita mo gidang rainbow, or rather nga ulan. If it's going to rain, and the droplets there are kind of large, usually hindi ta na makita, because it's not continuously suspended in air, but if it is a drizzle, nagatiner siya sa atmosphere, and when you have a drizzling droplets, so tiny droplets of water in the air, then you will see this dispersion of light, where light becomes trapped in that particle of water. So as light goes around that water and gets out, then you see the varied colors of the rainbow. So I think if you find a rainbow and you are flying, you will see it to be round. But in our perspective, when we are on the ground, we kind of notice that there's a starting point on our left, and then there's an end point on our right side. But actually, if you are elevated, you will also see it to be something like a circle. So a rainbow is an example of dispersion. Now, we also observe that in the fiber optic material, where we send our internet signal, our phone signals, when we call over our phone, our voice can be transmitted to this fiber optic, because we believe that light can be trapped inside that tube. The same way when we notice a fountain, a water fountain, why is there color when you let water be shaped like a curved water, like in a fountain? Why does the blue or the red color is following that shape of the water? Again, the same principle as your fiber optics. So you let light bounce inside, maybe through reflection, and then it cannot go out, so you trap it. And then therefore, if it's colored red on one end, then it will be following the red color all throughout. So again, the same thing. They use therefore light to bring the signal, a useful signal now from one end to the other. Okay, so again, a fiber optic is an application of the use of internal, no? So they call it as a total internal reflection. Total internal reflection is when a beam of light, no, in water probably, no, it's possible that from water to air it can still go up, but there's a certain angle there where you keep on increasing, no, the angle of incidence, and then therefore, no, the light will no longer get out of water, no. It will either, no, go straight horizontal to the right, or, no, when you keep on increasing it, then it will bounce back down, no? So this angle here that they call, no, where light cannot, no, refract anymore or cannot go out, as the critical angle, no? So once the critical angle is reached, there's no more refraction that will occur, no? So total internal reflection will happen, and light now will simply go back to the medium, no? So maybe here, no, in our fiber optics, that's what they do, no? They find the critical angle of the laser beam there, no, and then trap that laser, no, that is moving inside our fiber optic. So the fiber optic is actually, no, a material that is made of a lot of reflectors, but it's a very tiny, no, cylindrical wire, no. It's a hollow wire, no. So it's important that you will not bend it, no. So if you bend it, no, light cannot travel anymore, no. So they will always try to see to it that the fiber optic is always straight, no. Okay? So try to observe that in your house. If you have a fiber optic connection, the technician there will never permit it not to be tight, no? It has to travel, no, or it has to be placed, no, in an area where it cannot, no, be bended or tied, no, may bugkuson mo siya, no? So hindi na mag-ubra karon ang imong fiber optics if you do that, no? Here's another phenomenon about shallowing, no? So if you have a coin here and there's no water, you will not probably see the coin because the portion of the container that holds it blocks your view, no, of the coin, no? However, when you put water into the coin already, no, then the water now will cause the bending of the light, and it's possible, no, at a certain location, which may not necessarily allow you to view the coin directly, but you are able to view the coin, no? Because the coin will now appear, no, it seems to move upward, no? Doon naglutaw na siya pababaw, no, from its original, no, position. So if this is the line of sight, no, tadlong din siya, hindi mo siya makita ang coin lang, no? But once you put water there, then the coin now will appear to be, no, much more, no, nga do ara siya sa babaw sang aton nga bottom sang aton container, no. So you are now able to see the given coin, no.